Hello, and welcome back for another video on college algebra material. In this video, we're going to talk about polynomial inequalities. It's a relatively short section. The idea is instead of having a polynomial equation where we're looking for the x values that solve the polynomial, we have an inequality. This vastly increases the number of possible solutions because anything that makes it larger or smaller than the other side will work. And this opens up, well, in many cases, half of the real plane. So we'll solve these algebraically, and then we'll look at them on the graph so that you can see what the solution set actually represents. Let me share my screen with you, and we'll go ahead and get started. Now you can see that we have our first problem here. This is a polynomial inequality. It actually says that this line, negative 7x minus 2, is greater than this line, negative 4x plus 1. So instead of looking for discrete solutions, x equal 2 or x equal 5, we're looking for an interval of solutions. All of the x values in this range, in this interval, will satisfy this inequality. That's what you typically get when you're doing inequalities. So it opens up our solutions from a finite number of solutions to an infinite number of solutions that might work. Now what we're going to see is we're going to graph this in Desmos, and we're going to look and see what it means when we have one line above the other line. So you can see I have them graphed over here, and you can see that the first one is negative 7x minus 2, and the one in blue is negative 4x plus 1. We want to know when negative 7x minus 2, which is the line in black, is greater than negative 4x plus 1, the line in blue. So that would mean that the y value is greater than the y value of the other. And so you can see when we're looking here at this particular one, at these points, definitely the black is above the same y value on blue. But down here, that's not true. Here, the blue is above the black y value. So it looks like starting at this number and going to the left, then I have places where the black line is greater than the blue line. Now let's go through and solve this algebraically, and then we'll come back to Desmos, and I'll show you what it looks like when you graph the inequality. Coming over here, the first thing we want to do, of course, is rewrite the problem. Make sure to have everything there. So we have negative 7x minus 2 greater than negative 4x plus 1. Now there is a weird rule with inequalities, and it says if you multiply both sides by a negative number or divide both sides by a negative number, then you have to turn the symbol around. Now I'm going to show you how to get around that rule, and then I'm going to show you what it looks like if you don't get around that rule. In both cases, you'll get the same solution, but you got to be careful. Now, this only applies when you multiply and divide. So I try to avoid the rule when I can by adding and subtracting. Adding and subtracting negatives does not cause the symbol to turn around. So when I add and subtract to get all my variables on one side, I look for the smallest of the two variable terms so that when I move it, it becomes positive on the other side. So in this case, what I'm looking at is I'm looking at the negative 7x here, and I'm looking at the negative 4x here. So when I have the negative 7x and the negative 4x, negative 7 is to the left of negative 4 on the number line, so it's the smaller one. It is larger in absolute value, which makes it smaller when it's negative. So I'm going to move this one to the other side by adding the 7x to both sides of the equation. And notice on the right that positive 7x minus 4x will give me a positive 3x. If you always move the smaller one, it will always end up positive, which is nice. And then we have the plus 1. The symbol does not turn around. And on the left, we still have negative 2. Now I'm trying to isolate my x values. So I want to get x by themselves, but I've got to move things that are not as tightly attached. In this case, this would be the positive 1. So I'm going to subtract 1 from both sides of the inequality. And again, it balances here at the inequality symbol. So what you do, you want to do on both sides of the inequality. And this is going to give me 3x here on the right. I'm not changing the symbol because I'm subtracting. and adding and subtracting does not invoke that rule. And I get -3 on the left. Now I need to isolate x by dividing by 3. But the 3 I'm dividing by is a +3. So I have 3x divided by a +3. That does not invoke the rule, even though the left side comes up negative. The number I'm dividing by right here is a +3, so it does not invoke that rule. This is then going to give me that -1 is greater than x. Now, this really bothers some students. They don't like this in high school. It always came out on the left side, and they don't like it on the right. It means the same thing. -1 is greater than x. Larger meaning -1 is on the right and x values are on the left. Now, we can turn it around, but we have to turn the whole thing around. So if you visualize your symbol and you walk to the other side, notice that the symbol actually changes direction. So we're still going to have the narrow end of the symbol pointed towards the variable x and the wide end of the symbol pointed towards the number -1. Now this means that all our x values are less than -1, which is the same as saying -1 is greater than x. I'm taller than Jack. Jack is shorter than me. That says the same thing. So now what I want to do is I want to find all the values of x that are less than -1. On the number line, the far left is -infinity, and we go to -1. Now, it doesn't have the or equal to symbol on the bottom, and so we're going to use a round parentheses instead of a square bracket. With the or equal to, we use a square bracket because it could also be that number. Here, we don't have that, so it's round. Now, let's take a look and see what this means. This means that any x value between -infinity and -1 should make this line, -7x minus 2, greater than this line, -4x plus 1. Let's take a look over here on our number line. Now, I also graphed the inequality you can see right here. And when I graph that one and click on it, you'll see that it shades the entire region. And you'll notice that it is shading the region right here, if I can get on it, from -1 to the left. So all the values of x that are between -infinity and -1 will work. And notice this is also where we said the black line was above the blue line. That's what it means to solve a polynomial inequality where the sides happen to be lines. Let's take a look at another example. Let's now look at the next problem. You'll see here that we have another example where we have two lines, -6x plus 4 on the left and 7x plus 43 on the right. The inequality this time, though, is less than or equal to. So this time when we give our interval notation, we'll use a square bracket, not a round one, but square. And that way we'll include that endpoint in the interval. We're going to go ahead and solve this one algebraically first, and then we'll take a look at Desmos. So let's write it over here. We've got the following. Hang on while I get my screen set back up. Okay, so we have the equation -6x plus 4 less than equal to 7x plus 43. Now this time I'm going to solve it and I'm going to move the variable terms to the left, where a lot of students just, well, frankly, they just like them on the left. But when we do this in this particular problem, it's going to create a negative variable term. And then in order to solve and isolate for x, we're going to have to divide by that negative, which will reverse the symbol. So I'll show you how to do it this way, and then I'll show you the method of avoiding it by always moving the negative variable term, the smaller one. So now what I'm going to do is I'm going to isolate x by getting my x terms together. This time, instead of moving the smaller term, -6x, I just move them to the left. Now this gives me -6x minus 7x. Note that I'm keeping it balanced across the inequality symbol. And this gives me -13x plus 4, which is less than equal to 43. My less than equal to doesn't look quite right. There we go. Now I need to isolate the variable term with x in it by moving the +4 to the right. So I'm going to subtract my 4 from both sides of the inequality symbol. And this gives me negative 13x less than equal to 39. Now I want to isolate x by itself, so I need to divide by the negative 13, but the number I'm dividing by is negative, which is going to reverse the symbol. So when I have negative 13x and I divide by negative 13 on both sides of the inequality, what this does to the symbol is it reverses just the symbol, not the variable and the constant terms, just the symbol. So now it becomes greater than equal to. I know it's a tricky rule and it's hard to remember. This is going to give me x greater than equal to a negative 3. Now let's rework the same problem, but this time we're going to avoid that rule by moving the smaller of the two variable terms. So we're going to start back over, and I'll change colors so that you can see the new color. So we have starting back over at our original problem. And this time I compare the two variable terms, negative 6x and 7x. Negative 6x being negative is smaller. So I'm going to move that term by adding 6x to both sides of the inequality. There's the balance point. And this will give me 14 on the left, less than equal to 13x plus 43. Now the next thing that I need to do, is that a 14? That's not a 14, that's a 4. All right, good thing I caught it there. I was looking at it going, something's not right. Okay, so now let's move the 43 by subtracting 43 from both sides of the equation to isolate the 13x. So again, we do one on the left side of the inequality, one on the right, and that gives us negative 39 less than equal to 13x. Now I want to isolate x, so I divide by a positive 13, but the number I'm dividing by is positive, so the symbol does not turn around. It stays in the same direction. And this gives me negative 3 less than equal to x. In other words, x is on the large end of the symbol, so it's the bigger thing, and negative 3 is on the small end, so it's the smaller thing. And that's the same in both of the examples, or both of the expressions that you see here at the bottom, the one in blue and the one in black. In both cases, the x is on the wide end and negative 3 is on the narrow end. We start with the narrow end, so our solution step is going to start with the narrow end, and notice that we did in fact go ahead and use that square bracket because of the or equal to part of the inequality. And then we're going to go to the far right, which, well, how far does x go? Well, it goes to infinity. So it looks to me like the solution set would be negative 3 to infinity. Now, when we look at this on the graph, it's going to shade the part of the region where one line is above the other. So again, we're looking to see where negative 6x plus 4 is either equal to 7x plus 43, or where negative 6x plus 4 is smaller. So the y value is smaller. So we're going to come over here. You'll see negative 6x plus 4 is the black, and 7x plus 43 is in blue. Now we want the black to be lower than the blue. And I can't even see where they cross, so I'm simply going to drag it down until I can see it. I want the black to be lower than the blue. Well, over here, I can see that I've got black and I've got blue. So I want the black to be lower than the blue. I think that's correct, right? Negative 6x plus 4 greater than or less than equal to 7x plus 43. So I need this to be lower. Right here, it's not lower, it's above. So that's the wrong region. But here I've got the blue above the black, and they're separated really far apart. So it looks like from this value where they intersect at negative 3 to the right should be the solution set, which is what we got. Let's now graph it and see what it looks like. Yes, indeed, it is starting at negative 3 and using all values where x is greater than or equal to negative 3. And that includes any of these y values as well. All right, let's take a look now at our next problem. In our next problem, we have a line being compared to a parabola. So remember, the parabola basically opens up like this, and then we've got the line like this. In this case, we want the line 4x minus 5 to be below the y values on the parabola, negative x squared minus 5. Now, the parabola is going to open down because of the leading negative. So we want the line to be below the parabola. Let's go ahead and let's solve this one first. We're going to look at this one a little bit differently. This one has a quadratic in it, so we cannot use the approach that we used with just lines. We're going to have to use a different approach. We have both a negative x squared term and we have a positive 4x term. What we want to do is we want our squared term to be positive, and we're going to actually move everything to one side of the inequality, whichever one gives us that x squared term being positive. So we're going to start with 4x minus 5, and it's less than negative x squared minus 5. And I must have my finger on the erase button. All right, now I want to move everything to the left. This is different than what we did before. I'm going to move everything over here by adding x squared and adding 5. So this is going to give me plus x squared, which I don't write under the 4x because they're not like terms. And the plus 5 can go under the minus 5 because they are like terms. And then this will give me x squared plus 4x. Notice that I now have to write the plus. Negative 5 plus 5 is 0. And then less than 0. When I moved everything, it doesn't eliminate that side. It just makes that side 0. Now I've got a quadratic expression, x squared plus 4x. So what I want to do is I want to factor this. So we've studied factoring before, so I'm going to factor it. So I have x and I have x plus 4. And this has to be less than 0. Now, I know that these factors actually are associated with solutions, right? I know that if I were solving an equation that looks like x plus 4 equals 0, then I would have x equals 0 or x plus 4 equals 0, in which case x would be negative 4. So what I want to do now is I'm actually going to look at these two numbers on the number line, and I'm going to look at the sign of the factors in each region. So it creates like a table. These are actually kind of fun, I think. You look at the particular solutions for each factor. And so we're going to go ahead and we're going to write a number line. And negative 4 is to the left of 0. So make sure you get them in number line order. And here's 0. It doesn't have to be to scale, just create some space. And then we're going to look at these factors. So I've got the factor of x and I've got the factor of x plus 4. And then down here, when I combine them together, I want to see what I get when I have both x and x plus 4. So now I'm going to do each line in a different color. So when I look at x, if x is to the left of negative 4, well, then they'd be negative numbers. So I can put a negative there. And if x is between negative 4 and 0, well, they'd still be negative. But if x is greater than 0 to the right of 0, then they'd all be positive, right? What I'm actually doing here is I'm taking a test point. Like in this region, I could use negative 5. In this region, I could use negative 2 or negative 1. And up here, I can use a test number of 1. So I've got these 3 test numbers, and I'm plugging them into the factor to figure out if it's positive or negative. I don't really care about the number. I just want the sign. Because this says that x times x plus 4 is less than 0. Well, that just means it's negative. So I'm looking to see where that becomes negative. Now I want to look at x plus 4, and I'm going to do these in gray. So x plus 4, I'm going to plug in the test number, which is negative 5, into this factor expression, and I get negative 1, and all I really care is that it's negative. Then I'm going to take the test number for negative 2 and plug it into the factor x plus 4, and that's going to give me a positive 2. So that's a plus, that's a change. And then I'm going to take the last test factor and plug it in, and it's still a plus. Now I want to combine these signs together. So what I've got here is I've got a negative times a negative, which comes up positive. And then I've got a negative times a positive, which comes up negative, and a positive times a positive, which comes up positive. Now, what am I looking for? I'm looking for this to be less than 0, which means it's negative. And it's a strict inequality, doesn't have the or equal to. So where is the combination of x and x plus 4 negative? Well, between -4 and 0, and because it doesn't have the or equal to, then my solution is the interval, not the point. This is an interval, and they look the same. So you have to know from context which one you have. -4 to 0. This is an interval between -4 and 0. Let's now graph it onto Desmos, and we'll take a look and see if it makes sense when we get it out there. Okay, you can see that I've graphed the line -4x minus 5 in black, and you can see it right here crossing at -5 on the y-axis. And here is the downward opening parabola, -x squared minus 5. And you can see that it also has a y-intercept down here. Something's a little bit off. Oh, yes, at -5. All right. I thought that -6 was a -5. I was a little thrown off by that, but it's marking them off every 2. Okay, so what was I looking for? I was looking for where the line 4x minus 5 was below the parabola. So the line is below the parabola here, but if I extend down a little bit further, you'll see that the line then becomes above the parabola again down here. So I need to go between this value right here, which is at -4, and then if I scroll up a little bit to this value right here, which is at 0. So between the values of -4 and 0, the line is below the parabola. But when I get outside of that range, it is not below the parabola. And when I graph the solution, you're going to see that it fits within this band, right? So these are the values of x that will force the line below the parabola. And that's basically what we're doing. I hope you thought that one was kind of fun. Let's take a look at another one. I think these are kind of fun. I like the little tables. So now we have another quadratic with a linear, and this one does have the or equal to. Notice up here that when we had no or equal to, that it doesn't include the -4 and the 0. And over here, you can tell that in Desmos because it's got dashed lines on the edges. Let's see what happens now when we have or equal to. So go ahead and pause the video, work out the problem, then turn it back on, and we'll compare our answers. So this is actually kind of a trickier problem. Maybe I should have worked through this one with you. So I'll go through it pretty carefully. When we're looking at this one, you do have the choice whether to move things to the left or to the right. I chose to move them to the left, but that did cause my x term to be negative. Am I going to have to take care of that in order to factor it? So I moved the -3x minus 1 by adding 3x and adding 1. You can do both steps in the same step, or you can do them in separate steps. Notice that I did the same thing on both sides of that inequality. That gave me -x squared plus 9 less than equal to 0. Now, I don't like to factor with a negative on the x squared. So to fix that, I multiplied by a -1 on both sides. But when I multiply by a -1, I got to remember that tricky rule where I reverse the symbols. So I highlighted here that it was less than equal to, now it's greater than or equal to. Your other option from this step right here is to add x squared and subtract 9 from both sides. In effect, that also reverses the symbol because it puts the variable term on the wide end of the symbol. Either way, you should come up with x squared minus 9 greater than equal to 0. That means that it's either positive or equal to 0. So when we factor x squared minus 9, difference of two squares, we get x plus 3 and x minus 3. These have the two solutions, -3 and 3. We draw our number line, we put the solutions on in number line order, -3 to the left of 3. Then this divides the number line up into 3 regions. I pick a test point in each of the 3, any number in the 3, but make it easy. And then I take the test points and I plug them into each factor one at a time. For x plus 3, this gives me a negative, a positive, and a positive. For x minus 3, this gives me a negative, and a positive. Then I combine the signs together to figure out what this x plus 3, x minus 3 looks like. Negative times negative is positive, positive times negative is negative, positive times positive is positive. And I'm multiplying because the factor x plus 3 is multiplied by the factor x minus 3. Now, I was looking for positive or 0 because of the or equal to will include the endpoints. Where is it positive? On the far left up to -3. Far left is negative infinity, up to -3, square bracket because of the or equal to. Now, I'm not finished. There's another section. So I put a U symbol for union. It doesn't have a tail on it. It's just the U part. And then we pick up again at 3 and go to the right. So that's 3 and to the right is infinity. Notice negative infinity, if used, is always on the far left, and infinity, if used, is always on the far right. And again, we make this one a square bracket as well. Let's take a look now at Desmos and see what it looks like. Here's our line, -3x minus 1 in black, and here's our downward opening parabola, -x squared minus 3x plus 8. We want to know when is the parabola below the line or equal to the line. Equal would be these points of intersection here at -3, and I'd have to scroll up down here at 3. So when do I have the parabola for -x squared minus 3x plus 8 below the line? So when is the parabola below the line? Well, the line is here, so out in this region to the left of -3, that works. And then again, if I look down here, I've got the line above the parabola starting at this 3 and going to the right. So when I graph the inequality, you'll see that this time it makes these bars here at 3 and -3 solid because of the or equal to. To get the or equal to, simply type in less than and then equals, and we'll automatically convert it to less than or equal to. Let's go ahead now and turn our attention to the next problem. Again, we have a line compared to an inequality. This time, the -4x squared is on the right, and when I add it to both sides to move it, it will become positive. So I am going to move everything to the left. And then I'm going to take a look and see if I can factor the polynomial that gets left. Go ahead and pause the video, work it out, and then turn it back on and we'll compare. So how did you do? Let's compare our answers and see if we got the same thing. So when we set up our equation, you can see we have 8x minus 2 greater than -4x squared minus 4x minus 10. When it's this line, 8x minus 2, above this downward opening parabola, -4x squared minus 4x minus 10. We want to get everything onto one side of the inequality and then factor it. I went ahead and moved everything on the right to the left. And that gave me 4x squared plus 12x plus 8 greater than 0. Now, greater than 0 means positive only, but not equal to 0. So we should have dashed lines when we graph the inequality. Now, these each are divisible by 4. And so because they're divisible by 4, I can factor out the 4. Now, the 4 is not going to give me a solution. It's always 4. It's never 0. But it is a factor. And it will affect the solution set. Then we're left with x squared plus 3x plus 2, which factors as x plus 2 and x plus 1. Now we have three factors, 4, x plus 2, and x plus 1. And you'll see over here we have lines for 4, x plus 2, and x plus 1. Now 4 is never 0, so it doesn't give us a solution, not something we're going to mark off on the number line. But x plus 2 gives us negative 2, and x plus 1 gives us negative 1. These possible solutions to the equation become the numbers you mark off on the number line. Take a test point to the left of negative 2, negative 3, negative 4, negative 5, whatever works, and then something between negative 1 and negative 2. Now this one's a little tricky because there are no integer values there. So I took the easiest one I could, which was negative 1.5 or negative 1.5. Any number greater than 1 will work here, 0, 1, 2, 5, 10, whatever. Now, take each of the factors and substitute the test point in place of x. There's no x here, it's always positive 4, so it's positive in all three situations. Remember, this has divided our number line up into three regions. X plus 2, when I plug in the negative 3, I get a negative 1, so it's negative. At negative 1.5 plus 2, I get a positive 1/2, so it's positive. And at 0 plus 2, I get 2, so it's still positive. Then I test the factor x plus 1 by plugging in each of the test points in turn and writing down the signs. Have you noticed anything funny about when they change sign? Notice that x plus 2 changed sign at its solution, negative 2. That's when it went from negative to positive. X plus 1 has the solution, negative 1, and notice it changed sign at negative 1. Now, we don't know if it's going to go positive to negative or negative to positive. You're going to have to test to find out, but that is when it will change. Now we multiply all the factor signs together. Positive times negative is positive. So to the left up to negative 2, it's positive, but not including negative 2. At negative 2, it's 0. 0 is not positive and it's not negative. It has no sign. It's the only number that has no sign, kind of a special deal. Then we multiply positive times positive and negative, and that gives us a negative. That's not what we're looking for. We're looking for positive only. And then we have a positive times positive, which is positive. So again, from the point on the number line, negative 1 to the right, we have positive values. Don't include negative 1, it's 0 there. So this gives us negative infinity to negative 2, union negative 1 to infinity. Another thing that you can do is you can mark off on the number line, and I'm trying to get the right color. We want to go to here, and we want to go to here. But we don't want to include those numbers. We want them to be empty because it's not or equal to. Notice that this pattern right here matches what we have in the interval notation. Far left is negative infinity, stopping at negative 2. Not finished, so union symbol, picking up negative 1 and moving to the right to infinity. I hope this makes sense to you and that you're understanding how to solve these rather challenging problems. Let's take a look at another problem. Now, this next problem is a little bit different in that both sides of the inequality are parabolas. In fact, they're both downward opening parabolas, but the meaning is the same. When is the parabola, in this case on the left, less than equal to the parabola on the right? So we know equal to means that they intersect, that's where they touch. So less than means that the graph of the one on the right is above the one on the left. So let's go ahead and solve this one the same way we did before. We're going to move all the variable terms and all the constants to one side. We're going to make sure that our leading coefficient is positive. We'll have to multiply by a negative if it's not. And then we're going to factor it completely. Take each factor, find the solution, create a number line, and then test each factor with a test point to find the sign, positive or negative, in that region. then combine all the factors together to see what it is for the final solution. Go ahead and solve this one, and then we'll compare our answers. Okay, let's compare our answer. This time it was relatively easy and straightforward to move everything to the left. It did result in a positive 2x squared term. So I didn't have to multiply through by a -1 and reverse that symbol, which is super nice. Now it did give me coefficients that were all divisible by 2. So I factored the 2 out to make it easier to factor. Now, the next thing I can do is I can factor the resulting trinomial x squared plus 6x plus 8 as x plus 4 times x plus 2. Now, this is all less than or equal to 0, which means negative or equal. That means we'll use square brackets and solid circles, filled in dots. Now, 2 is never 0, it's always 2. And we'll see over here in the line that it's always positive 2. X plus 4 gives us the solution -4, and x plus 2, the factor, gives us the solution -2. When you mark off -4 and -2 on your number line, be sure you mark them off in number line order. -4 is to the left of -2. This will help to ensure that your interval follows the correct order. We create one line for each factor, and then the last line is the combined factors. 2 is always positive. X plus 4 with solution -4 will change sign here at -4. When I plug in -5, I get -1, so it's negative, which must mean it's positive thereafter. It's a line. Once it changes sign, it never changes back. X plus 2 has the solution -2, so it must change sign here between these two sides. When I substitute the test number -5, I get -3, so it's negative here. And again, you can substitute the test number, or you can realize that it's not going to change sign until it gets to its solution, -2. So it's got to stay negative. Then it changes sign. And again, 0 plus 2 is +2, which gives me the last sign. Then we multiply the factor signs together. We get a positive on the far left. We get a negative in the center and a positive on the far right. Now, we're looking for things that are negative or equal. Equal means that our two numbers that divide our regions are going to be filled in with solid dots, and we'll use square brackets. Now, negative falls in the region in the center between -4 and -2. Follow your number line to write the interval. On the left is -4, on the right is -2. Let's take a look at Desmos and see what this one looks like. Well, we do have two parabolas, but the numbers are so large, it's really kind of hard to tell which one is which. We're looking for when this one in black is less than or equal to this one, which is going to be in blue. So when we're looking for this, we're looking for when the black is below the blue. So blue has to be on top. Well, in most of this region, it looks like black is on top. But right here in this tiny sliver of a section, we have blue above black. But it's really hard to tell where they're intersecting. And you can kind of see it, and Desmos will help by wanting you to click on that intersection point. And we can see this is at -2. That corresponds to what we found here in this particular one with the -2. Now, where's the other intersection point? When we look at the other intersection point, it's so hard to find on Desmos. This is why graphing is a terrible way to solve these problems. Algebraically, you can always get the precise answer, and it's much better. It looks like it's in here, but I can't tell exactly where. But again, Desmos wants me to click on it and will give me a ball at the precise point of intersection. This is going to be from -4 to -2. And when I graph the inequality, you'll see that it has solid lines on either side. And this is going between -4 and -2. And we know then that we have solved this correctly. Let's move on to our next example. This next example is again going to be a parabola and a parabola. So we have a parabola on the left greater than the parabola on the right. Pause the video, work it out, and then we'll compare our solutions. Okay, let's take a look at the solution for this one. Again, we have a parabola on the left and a parabola on the right. This time I chose to move the left to the right because I knew that moving 3x squared instead of 7x squared would result in a positive x squared term. And that gave me 0 greater than 4x squared plus 8x minus 32. Now the problem is I don't really like the 0 on the left, but I can turn the whole inequality around if I keep the same end of the symbol pointed to the 0 and the same end of the symbol pointed to the expression with x. This way, I've got the narrow end towards the x, and here again I have the narrow end, but now I've written the quadratic expression on the left, and then I have the 0 on the right on the wide end of the symbol in both cases. That preserves the sense of the inequality. It's just like instead of writing 5 equals 10 divided by 2, you write 10 divided by 2 equals 5. All right, then I've got a common factor of 4, which I factored out, and then I factored the trinomial, which gave me x plus 4 and x minus 2. These have the solutions -4 and 2. Make sure to mark -4 on the left and 2 on the right. We have factor 4 by itself, which is always positive. Factor x plus 4, which changes sign at -4, and is negative when we use the test point -5. Thereafter, at the other test points, it's positive. The factor x minus 2 will change sign at its solution too. At -5 for the test point, it's negative, and at 0, it's still negative. But at 3, it becomes positive. Now, because we're looking for the product of these 3 factors, we multiply their signs together to get the sign of the result. Positive on the far left, 0 or negative in the center, and positive on the far right. We're looking for something less than 0 or negative, not equal to. So we have an empty circle here, an empty circle here, and it goes in between. Your interval should look like this, and you'll use round parentheses because it wasn't or equal to. -4 comma -2. Now, how do you know this isn't the point at -4, -2? You only know from the context. This means all the x values between -4 and 2. Is it? Oh, not -2, 2. Good catch. All right, so -4 to 2. You can't tell by just looking at it. You have to know from the context of the problem you were solving. Now I want to work 2 more examples here, and I want to kind of show you, well, maybe 3. I'm going to make up a couple, and I want to work 1 more from the problem set. So let's turn our attention now to problem number 10. The others are pretty much the same as what we've been doing, but number 10 is a little bit different. Let's scroll down and find number 10. How is number 10 different than what we've seen before? Well, this time on the left, we don't have a quadratic or a linear, we have a cubic. Remember, the cubics kind of look like the whole John Travolta thing where it's going up and then it kind of flattens and then it goes up. Or it goes up and it does a wiggle and then it goes up, right? But basically the end behavior is like this. And it's either flat in the center or it has a wiggle to it. Now, we don't know what this one looks like, but we want to know what x values cause this cubic to be above the graph of this parabola, this quadratic equation. Again, we're going to approach this the same way we've done before. This time we're going to move everything to one side, just like before, and we're going to try to factor it. But because it's cubic, we may have to use the rational zero theorem that we covered in the previous section. Let's go ahead and start this problem. You may want to pause the video and see if you can factor it, and then we'll compare our answers partway through. All I've done is the first step here. So I went ahead and moved the quadratic to the left side of the equation by either subtracting if it was positive or adding if it was negative. And this gave me 4x cubed minus 8x squared minus 20x plus 24. Now I do have a common factor of 4, which I can factor out. So let's do that now. This will give me x cubed minus 2x squared minus 5x plus 6. Now, I can try to factor by grouping. If it doesn't work, however, my only option is to use the rational zero theorem to try to factor it. I know from the fundamental theorem of algebra that it does factor because all polynomials with integer coefficients have to be able to be factored into linear terms, x to the first, and quadratic terms that don't factor further, x squared. And this has an x cubed, so I know it has to factor. So the question is, how does it factor? Well, if I look and I group these two together, then the problem is if I take out an x squared, I'll get x minus 2. But these two have nothing in common. When I factor out the negative, it won't give me x minus 2. So that didn't work. If I group x cubed with the minus 5x, I can take out the x and get x squared minus 5. But when I group the negative 2x squared and the 6, and I factor out a negative 2, I get x squared minus 3. That's not the same. In other words, no matter how I look at this one, I have one more option to try, x cubed with 6, but these two, they're not going to give me anything that factors by grouping. So I'm kind of stuck. What do? Rational zero theorem. So now we're going to take the rational zero theorem and we're going to find what possible roots that are rational numbers that this one could have. Remember, it comes from the factors of the constant term at the back. So all the positive and negative factors of 6 divided by all the positive and negative factors of the leading coefficient. We've already factored the 4 out, so now the leading coefficient is going to be the number multiplied by x cubed in the parentheses, which is 1. So this basically gives me plus or minus 1 times 6, plus or minus 2 times plus or minus 3. Oh, and I forgot my plus or minus on the 6. All divided by plus or minus 1. Well, any number divided by 1 is itself, so this gives me basically plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. In other words, I've got 8 different numbers to try. What are we looking for? We're going to do synthetic division, and we're going to look for one with a remainder of 0. That means it factors it completely. Or you can do each one as a factor and use long division. I'll leave that up to you. In order to help me solve this one a little bit faster, I'm going to use Desmos to predict which one it is. And then I will be able to work it a little bit quicker. So I'm going to actually graph this cubic, not including the 4, just the x cubed minus 2x squared minus 5x plus 6. And I'm going to look for the x-intercepts. Those would be the exact zeros or the solutions. If I find a rational number, it's got to be one of these in this list. So let's go ahead and factor it now. You can see that I have graphed the cubic right here in the directions for Desmos, and you can see that this is a cubic that wiggles. It opens generally uphill because it's a positive x cubed. Now, it does look like it crosses at negative 2, and yes, Desmos agrees, negative 2, 0. It looks like it also crosses at 1, and it looks like it also crosses at 3. I can choose any one of those to test for. The easiest would probably be the 1. The negative would probably not be, but it looks like I've got it factored here. I'll show you another way to shortcut this, but I want to demonstrate the synthetic division. Without graphing it on Desmos, you're going to have to try all 8 numbers until you find one that has a 0 remainder. Let's test one since we know it's a solution. We're going to take the coefficients of the cubic in descending order. So 1, -2, -5, and 6. 1, -2, -5, and 6. Remember, if it's missing a term, you have to fill that in with a 0. And then the first number drops through. Then we multiply diagonally to the left, and then we write it up here diagonally to the right. So 1 times 1 is 1, I write 1. Then I'm going to add down, so I get -1. And then I multiply diagonally again and write it up here, so I have a -1. Add down, I get -6. Multiply diagonally this way and write it here. I get -6, which is a remainder of 0. Box off the last number, that's the remainder. That's the y value when you use x = 1 in that cubic. It worked, and because this was x cubed, this becomes 1x squared minus 1x minus 6. Now we want to factor this. So what we've done is we've taken this one up here and we've rewritten as 4 times. Well, now what's the factor that goes with the solution x = 1? If you back it up, you get x minus 1 = 0. So we have x minus 1 times x squared minus x minus 6, and we want this to be greater than or equal to 0. Now you could test the other two since you know that they're probably solutions, or since this is now quadratic, we can simply factor it as it is. And when we factor it, we get x minus 3 and x plus 2. This gives us the remaining 2 solutions that we saw in Desmos of 3 and -2. So the 3 solutions that I have are 1, 3, and -2. I'm running out of space, so I'm going to put them up here. This will give me x = 1. X minus 3 will give me x = 3. And x plus 2 will give me x = -2. 4 is not 0, and so it doesn't give me a point to mark off on the number line. Look up here and decide which one is the smallest. That would be -2. That's going to go here. Then what goes next in the number line order? 1 and then 3. Again, these don't have to be to scale. Now we want to take some test points. And I probably need to move my 3 over because it's getting kind of close to the side. Below -2, I have numbers like -3, -4, -5. Between -2 and 1, I could use -1 or I could use 0 are the easiest, 0 being the easiest. Between 1 and 3, the only easy number to pick is 2. Notice that I now have a 4th region, which is to the right of 3, so I could pick 4, 5, 6, etc. Now I need to write down my factors. So I've got the factor 4, I've got the factor x minus 1, I've got the factor x minus 3, and I've got the factor x plus 2. And then I need to have the combination of all of them. Oops, that's supposed to be a minus. And x minus 3 and x plus 2. Now let's use our test points. We know that 4 is always a positive 4. So in all 4 regions, it stays positive. Then we can look at x minus 1, which we should predict is going to change sign here at 1. But I don't know what sign it has here, so use the test point. -3 minus 1 is -4, so it's negative. 0 minus 1 is -1, so it's negative. I predict it changes sign here and becomes positive because 1 is the solution to the factor x minus 1. Testing 2, I do get a positive, and this is also positive. Apply the same thing to the factor x minus 3, which I predict will change sign on either side of the 3 because 3 is its solution. -3 minus 3 is negative, 0 minus 3 is negative, 2 minus 3 is still negative, but 4 minus 3 is positive. I still have one more. So now I'm going to do another one. And x plus 2 should change sign at its solution, which is -2, the first one. -3 plus 2 is a negative number. 0 plus 2 is positive, 2 plus 2 is positive, and 4 plus 2 is positive. Now we multiply the signs of all the factors together, and we write that down here next to our product of all the factors. Positive times negative times negative times negative is an odd number of negatives, so it's negative. Positive times negative times negative times positive is an even number of negatives, so it's positive. Positive, positive, negative, positive is an odd number of negatives, so it's negative. And all positives give me all positives. Now, what were we looking for? Well, we were looking for greater than or equal to 0, which is positive or equal. So now we're going to look for the regions where it was positive, and we'll include either end of those intervals with square brackets. So the positive regions are here and here. So we know we want this region here and here going to the right. That means that we need to include this point here, -2, and this point here, 1, and this point here, 3. So when we write our solution, we want to follow this order that we see right here. We want to follow it in number line order. So we start at the left, and the first thing I have is a ball at -2. So square bracket -2, which continues until I get to 1. And then it's a ball, so I make it a square bracket again. I'm not finished, so I put the U for union symbol, meaning basically there's more to come. And then I have a solid ball at 3, and it goes to the right without end, so forever. So I'm going to have a square bracket at 3, and infinity is always on the far right. I hope this makes sense to you and that you're understanding better how to solve these polynomial inequalities. Now, there are a couple of other cases that I want to consider. So let me see if I can create these two cases for you, and then we'll look at these special cases. Okay, I've created my special problems for you to show some special cases of what can also happen. So in this particular problem, we're looking at two parabolas, x squared plus 2x plus 3 and -x squared minus 4. Now we want to know when the parabola x squared plus 2x plus 3, which opens up, is less than -x squared minus 4, which opens down. Let's go ahead and solve this algebraically, and then we'll look at Desmos to see what it means. In this case, the easiest thing to do would be to move everything to the left by adding the x squared and adding the 4. Note that I line up like terms under like terms. Don't put the plus 4 under the 2x. They're not alike. Put it under the plus 3. This then will give me, well, what does this give me? This will give me a 2x squared plus 2x plus 7 less than 0. Now I'm looking at this problem and I want to know, when is this going to be less than 0? Unfortunately, this is not one that factors. It is in fact prime, or what we call irreducible. So what do? Well, I look to see where it crosses the x-axis. If it doesn't factor, I can still find them, but by using the quadratic formula. So let's test it and see where it crosses by using the quadratic formula. So when I do that, I'm going to have a equal to, b equal to, and c equals 7. I'm looking where this parabola, which opens up, is below 0. That's equivalent to the equation that we had at the beginning. So now I'm going to solve for where the x-intercepts are by taking the opposite of b and dividing by 2 times a, and then adding and subtracting the square root of b squared minus 4 times a times c, which I never do in my head, even after all these years, and I divide that also by 2 times a. Now this is going to give me a negative 2 divided by 4 plus or minus the square root of 4, and I'm in trouble because I can tell that what I have under the radical is going to be a negative number. Well, it is a solution. It does solve the equation. It's just not a real number, so it doesn't show up on the real number line. Well, that must mean that this parabola never touches or crosses the x-axis. So it's wholly above or wholly below. And because it opens up, it has to be completely above. In other words, there's no solution to this. There's no value of x that will make this become negative. Let's look at the original problem and see what happened. We have x squared plus 2x plus 3, our upward opening parabola here in black. We have negative x squared minus 4, our downward opening parabola here in blue. Now, the original problem was, when was x squared plus 2x plus 3 below, less than, negative x squared minus 4? Well, is the black ever below the blue? No. What would happen if I graph the inequality? I get nothing. Nothing shows up because there's no solution. So how do we write no solution? Well, you can write it out in words. I often abbreviate solution SOLN, or you can give what's called the empty set, which looks like a 0 with a slash extending above and below. This is the empty set. Or you can write it in empty curled brackets. There's no solution, nothing. So the next thing we want to do is, what would happen if I reverse this inequality? What if instead of less than, it was greater than or greater than equal to? Let's take a look at the same parabolas, but this time with the inequality being greater than or equal to. Well, when we solve it, we're going to end up with exactly the same thing we did here, 2x squared plus 2x plus 7, but it will be greater than or equal to 0. So now we have 2x squared plus 2x plus 7 greater than or equal to 0. But that one's always above 0. And when I come over here to look at the pictures, it's again asking, when is the black graph above the blue graph? And the answer is always. So when I graph this inequality, I get everything, all possible values of x. So how do I write this solution? I can write it different ways, which would be negative infinity to infinity, which includes all the numbers that are on the real number line. Or I can write all reals. Or I can write what's called a double bar R, which stands for all the real numbers. All three of these mean the same thing. Probably WebWork or your homework system will want it to be in this form right here, which is interval notation. I hope this video is helpful, and I hope you'll join me for the next one in the series. Until then, I'll see you later.